5-5, day 2. Really 3 examples total that are going to cover 4 slides. Really what I've got for you is another example, I should say, an application with a double angled formula. Then I'm going to show you kind of our last set of formulas for the chapter called the half angle formulas, which, as the name suggests, does something very similar to the double angles, the double angled formulas. It just involves the relationship of a half angle. And I got 2 examples of that, and that's it. All right. Part A here is taking this, okay, this equation, which models the distance of this kick based on the velocity and the angle that it was kicked from. Okay? We know, you may not be able to see all this. Let me move this over some. Cuts into the diagram some, but there you go. I was getting to part B, where the question is the angle for the ball to travel 200 feet. First, though, in part A, it wants me to write this equation in a simpler form. R is the length of the kick, all right? And I'm thinking of a double-angled formula because it's got this product of sine times cosine. The issue is I don't have a 2, all right? So this is a crazy little step to make here that you probably wouldn't see yourself and maybe do. But 1 over 16, I'm going to write that as 2 over 32, which is a little bit funny because I've changed the fraction to write it in, not its simplest form. So that's kind of interesting. But I have a reason for it. Okay, and a lot of times that just step kind of freaks people out, and they're like, what did you just do? All I've done at this point is, in the model, there's a constant of 1 over 16. I switched it and said it's 2 over 32, which is absolutely fine. I mean, 2 over 32 is the same value as 1 over 16. Okay? Now, I'm going to take the 2 over 32 and split it up. There's our initial velocity. And then I'm going to put 2 sine theta cosine theta. All right, so at this point, what has happened is I just basically took my 2 over 32 and split it up as 1 over 32 times 2, which if you pause for a minute and think about, I think you'll be convinced that that's the same thing, okay? Just off to the side, if you need to, do 1 over 32 times 2 over 1. Okay, you'll get 2 over 32. Now what has happened is 2 sine theta cosine theta. So these aren't going to change. 1 over 32 is still going to stay there. The initial velocity. But now with the double angle formula, I can make a substitution that this part right here, if you check your double angle formula for sine, you'll see that matches perfectly. And now I get it down from 2 trig functions to just 1. Okay, from 2 down to 1. And that's the simpler form that we were looking for. Okay? So now in part B, we have a distance, which is 200 feet, and it said the initial velocity was 80 feet per second. So basically I've got values for r and v sub 0. And I want to solve for the angle that it would have to be kicked at. And after making that little simplification with the double angle formula, it's going to be a little bit easier to do. And again, the big thing I did is in the original form, this is what I kind of didn't like, right? There's other ways of dealing with that if we have 2 different trig functions. The first possibility, though, is to factor, and that didn't look like it was going to work well with this problem. Okay, so next up here is I'm solving 1 over 32 times 80 squared. That you can just throw into a calculator all at once. Comes out to be 200. You can either believe me or throw it into a calculator and check yourself. Either way, divide both sides by 200 and we get 1 equals sine of 2 theta. Okay, this is where we do an inverse. Okay, inverse sine of 1 would give us 90 degrees. Okay, that you could get from the unit circle, or again, I do recommend using the calculator because I think it reinforces the concept of the inverse a little bit better. Now, I'm not forgetting about my second case. Okay, remember with sine, it's 180 minus your first answer, but I'm just kind of thinking a step ahead. And I'm not really interested in that second case because, I can get 2 different solutions. But the ones we've been solving, we've done a lot of just theoretical problems that didn't have an application setting. Okay? But many times when you're actually doing a problem in context, you kind of have a sense of which answer that you are looking for. Okay? Now here, 180 minus 90 is just 90 again, so this second case wasn't going to add any new solutions. And my last step is a breeze, just divide by 2. And there you go. To get that ball to go 200 feet at 80 feet per second, launch angle's got to be 45 degrees. That's the angle that'll do it. All right, so we're switching gears here to what we call our half angle formulas. All right, we'll talk about the plus minus thing. They're not a super pretty looking set of formulas. But notice it's got this relationship of the angle over 2. Okay. Whereas the double angle was 2 times the angle. All right. Basically, what we're gonna do with them is we'll do one application with some solving, because all these formulas can potentially be used in solving to simplify an equation, and then we'll get an exact trig value, and that's been another big theme throughout the chapter as well. All right. I picked one that we've actually already done. I think we did this. Maybe we haven't, but I'm pretty sure we did. The sine value of 105 degrees. All right, so somewhat of a familiar problem, though I think the last time we did it, we took the sum approach and we split up 105 into 60 plus 45. Okay, I'm going to take a little different approach here. Here's how I'm going to obviously use a half angle formula to do it. So if you're looking at this one thinking, couldn't you use the sum formula? Yeah, you could. Okay, and a lot of these, and honestly, it should be to no surprise. There's many ways to do these. Okay, so if I'm going back to my formula, I need to kind of think about what u is, and I'm going to say that u is 210 degrees. All right. I'm just kind of getting it set up to use a half angle formula, because at this point I haven't really said anything all that enlightening, just that 105 is 210 divided by 2. Okay, you probably already knew that. All right, but that means that u is 210. All right, and now I got to get into this whole plus minus thing. Just think about your quadrant. Okay, over here to the side. Right, I'm just thinking, all right. 105, right, that would be like right here. That's in quadrant number 2. Sine values are always positive in quadrant 2. So that plus minus, you just have to think about which one do you want. As always with the sign of a trig value, think about what quadrant you're in. I'm in 2, sine's positive. Okay, so I know I got a positive answer here. Still underneath the square root. Notice that I picked 210 to specifically set this up with an angle that's on the unit circle. Okay, so there I make the substitution, and we technically have an answer here, though we've got a little bit of work to do with it. I'm going to start with this. Minusing a negative number is like adding a positive. Okay, and now this step's a little bit weird, but down in the bottom, this is over square root 2, and as always, I want to rationalize the bottom. Okay, so if I do that, square root 2 times square root 2 is 2. Now up on the top, think of this as, like, all we're doing here is multiplying underneath the square root. All right, so I'm taking this 2 and multiplying by that 1, so I would get 2 plus, okay, at this point, the 2, when I multiply it by square root 3 over 2, all that's going to do is cancel that 2 down there, and we'll have 2 plus square root 3. Okay? Interesting looking number. It's got a fraction with 2 square roots, but right, that's what we were after, is to the exact value of the sine of 105 degrees. Last problem of the chapter. Let's do a little bit of solving. And this is right after seeing the half angle formulas, so what I'm hoping you see on the right side, and again, as always, let's stay consistent that we're going to solve in degrees, but I've got 2, and this is going to be an interesting little thing to do. You know, I've got cosine squared of x over 2. I'm going to go to my cosine half angle formula, and I'm just literally going to substitute the whole thing in. Right, and that substitution was right there. Okay, notice the squared is still there, and so from the formulas that you got up above, you should see a cosine of u over 2. In this case, u is just x. That's the name of the variable. Okay, and what that does is it gets me out of that x over 2. In a minute here, I've got to deal with another situation that I have 2 different trig functions, but kind of one thing at a time. Now, the plus minus is weird, but keep in mind that whole square root is squared, so I know it's going to be positive. Okay, so that square gets rid of the negative, gets rid of the square root, and times 2 and divided by 2. That whole right side is really just 1 plus cosine of x, which got rid of the x over 2, but now I've got a new issue I've got to deal with, that I've got sine squared, and I'm kind of all in on switching this whole thing to cosine. So this will be minus 1 plus cosine squared, which equals 1 plus cosine of x. Okay? It looks like I'm headed towards factoring, so I want to get everything over to the left side and get the right side to equal 0. I'm going to start with my cosine squared term, and then I only have 1 cosine of x. Now, interesting thing with the constants, on the left side I have 2 minus 1, but then I'm going to minus 1 again from the right side, and all the constants just cancel out. I'm still left with something that's factorable. I have 2 terms that each have a factor of cosine of x, which will leave me with cosine of x equals 0, and then cosine of x equals 1. I'm only looking for answers from 0 to 360, so this is the point where I apply my inverse. We'll start over here, right? Once we have it factored, we have to basically treat these 2 equations separately. Cosine of 0 is 90 degrees, and then jump down and check case number 2, which does yield a second solution to 70 as well. Cosine equals 1 at 0 degrees, right? Now if I take 360 and subtract my first answer of 0, I get 360, which appears to give us a new solution. But if you look at the notation really closely, it says 0 to 360 including 0, not including 360, because that's basically the same point. It's the same point on the unit circle, so cosine x equals 1, we'll just add one solution, and that would be 0.